Good afternoon and welcome to this Green Drinks session, a great tradition that SEDA has upheld for many, many years. My name is Sandy Halliday. I am the principal of Gaia Research. I'm a chartered engineer and I work on the boundaries of architecture and engineering, for which I've received honorary fellowships of both the RIBA and the RIAS. And I am very honoured to be invited to open the session this evening. My thesis is that our attitude to ventilation and the consequent impact on the internal and external environment has changed over time. Design solutions should be human-centric and context-dependent, but have tended to be dominated by short-term imperatives and prevailing cultural norms, trends or fashions. In Scotland, Lang may your lung week is a much beloved cultural blessing for a long, prosperous and healthy life. It tells me that comfort, wealth and health have long been recognised as correlated, if not a prerequisite for, then certainly vital components of our durability, our personal sustainability and that of our genes. Without a good lung, there is a bit of an issue with smoke. But in, say, 1200 AD, with a Scottish population under 500,000 and a global population of 300 million, there would have been confidence in the benediction. Average Scottish life expectancy was about 30 years. Burning peat or timber in a confined space was doubtless problematic, but being cold and poor was considerably less likely to enhance your longevity. A smoking chimney was to be esteemed as a sign of conspicuous wealth and ostentation, the Barber handbag of its day. Plus, a good chimney in a southwesterly wind sent combustion products to Scandinavia. Today, a global population of nearly 9 billion means that whilst the Chinese are burning filthy coal to make our solar panels, we all catch a dirty breeze. A sort of act local, stuff global initiative. Now we have new problems. Domestic mould causes huge harms, particularly to the vulnerable, and climate payback strikes randomly. Many commercial buildings are wasteful, and problems of building overheating are increasing. Essentially, we ventilate to improve thermal comfort and indoor air quality, and to preserve buildings. But provision of fresh air is known to be vitally important to individuals' perception of a space, their health and well-being, and their productivity, which introduces its own issues. So, to more recent history. Energy used to be cheap and free of adverse impacts. The energy crisis of the 1970s led to a massive increase in the price and to increasing attention to energy efficiency and to the sealing up of traditional air routes, such as chimneys in domestic buildings. No one thought much of ventilating a bathroom or a kitchen beyond propping open a window. In parallel, there was a trend for commercial buildings to be built with deeper plans and lower ceilings than traditionally. Deep plans required air to be transferred to the centre of spaces, often through the ceiling voids, lowering the ceilings further. The mechanical ventilation systems themselves introduced pollution. Windows were fixed closed, mechanical ventilation and cooling had effectively replaced natural systems. Temperature and humidity were regulated within narrow bands, established by the mechanical services sales team generally, and over which occupants had little or no control. This is when the fashion was for internal environments to be reduced to a profitable, artificially engineered box. It got messy. It still is. At the same time, synthetic materials were replacing natural ones, the combined cocktail effect of which was, and is still, largely unknown, although probably very bad. Little monitoring of internal pollution has ever been done. If you want to know more about this, then I suggest and heartily recommend this film under Cash Delson, which talks about the chemicals inside us. The approach to ventilation came under scrutiny when ventilation was identified as a very significant aspect of the running cost and environmental impact of many buildings, largely due to the use of electrical energy. Cost analysis highlighted technical systems as a significant proportion of the initial cost of buildings. 30% was not unusual, and they took up valuable space. Many of you will have come across this diagram that shows how the services actually have an increasing impact in terms of cost over time because they need to be maintained and replaced. There was increasing complexity. Controls had a lot to answer for. They were often generic, as in you would come into a space and put your hand down a load of switches in order to get to your desk at the far end of the room. They were non-intuitive, they were not obvious, they were often obscured behind things, they were certainly inflexible, they were incomprehensible quite often, they had high energy defaults, and they quite often turned unneeded systems on. Occupants were often dissatisfied with the lack of control over their environment. Poor ventilation systems were often associated with poor indoor air quality and a range of sicknesses which became known as sick building syndrome and later building related ill health. This showed as high absenteeism in unhealthy business premises and breathing problems related to mould and moisture in housing. Essentially, ventilation systems were using capital and space and running costs to replace the larger, taller rooms which had performed quite well without them, and they were making people sick. And then, of course, for many years, design and regulatory effort to make buildings more energy efficient focused on improving heating and insulation. As a consequence, the proportion of heat loss through infiltration has increased as these insulation standards have improved. Internal and solar heat gains have increased in many buildings. Lightweight construction makes them less able to store and lose heat. And of course, the climate is getting warmer. The outcome is an overriding, muddled message that both leaky buildings and tight buildings are bad, but necessary. And then came some research for those who were listening. There was a marvellous project called Solarbow, in which the intention was to design out the building services by attention to design at the early stages. And the outcomes were very useful. It showed that building costs came down, it showed that energy demand came down by 50% or more, and that usable floor areas actually were very attractive. It also reinforced something that I have felt throughout my engineering life and was well put by Rolf Jakobsen from Gaia Jumma. You can give a lifetime guarantee for every piece of technology that you don't install. I myself, in the very early 90s, was involved with a project at Oxford County Hall. It was a refurbishment, and the people working in the County Hall decided that they wanted to return to a natural ventilation system with local control rather than keep the existing air conditioning. They were prepared to tolerate the noise and the pollution in the city centre. This was reinforced by the fact that they had a certain level of control within County Hall for these issues, and they wanted to set long-term strategies for traffic management to reduce that noise and pollution, which shouldn't really be there in the first place. Within SEDA, there was some fantastic forward thinking. For example, Jed Penton put on this wonderful event, which is about looking at vital building syndrome, not what makes buildings sick, but what makes them designed for health. I worked with Howard and with John Gilbert to produce a design guide for detailing toxic chemical reduction in buildings to promote healthy internal environments and to minimise future liabilities associated with their disposal. It caused quite some consternation, particularly amongst the plastics community. There was work done on the occurrence of asthma, which was traditionally related to the external environment, to traffic and such like. What became clear was the incidence of asthma was the same on the Isle of Skye as it was in central London, and this allowed a focus to come back to the common factors such as the homes that children were in and spent a significant amount of their time in as potentially being a very strong interfering factor. There's a rising interest in moisture management and the potential for moisture buffering materials to buffer oscillations in relative humidity. So this is an example of the internal RH and the external RH in a building in the borders. It was shown in practice by designers using clay in bathrooms, which actually absorbed and buffered the moisture there, meaning that things like your mirror didn't steam up. I also undertook some work into air quality and health for people with dementia, and this was both related to the very high occurrence of breathing related ill health amongst older people, but also giving attention to the buildings that people were in, because one of the things which is vitally important to people who have mental disabilities and problems such as dementia is they really enjoy visitor time. But unfortunately, many of the environments that people are in are unpleasant, badly ventilated, and people really do not want to stay very long. And we looked at a number of design approaches to increasing the amount of air that you can get into buildings without that having a significant energy penalty. And there are some case studies that I could discuss. Now, the tradition of design thinking has moved again away from fully managed mechanical design solutions to an understanding of context, natural process, and awareness of human factors. Commercial buildings have moved to a much greater flexibility, hence the appearance in recent years of what has become known as mixed mode or hybrid strategies. These combine approaches rather than provide one fixed solution for everywhere. Mixed mode also means tragicomic, which it can be if it's done badly. Domestically, increasing interest in passive house with the requirement for mechanical ventilation with heat recovery has tended to muddy the waters again. Certification requires MVHR to be installed, and this sits uneasily with those who have experienced problems with automatic and dehumanised controls in the past. Whilst the energy modelling aspects have proved to be useful and robust, the fact that there is no requirement for consideration of material specification or passive moisture management means that this is still very unsatisfactory. In truth, neither mechanical ventilation or natural ventilation offers a panacea. Poorly controlled mechanical ventilations can use a great deal of energy to little effect. Air movement consumes a lot of energy, and frost protection can be a huge hidden expense. If badly maintained, they are a source of pollution. Natural ventilation can also introduce pollution if sited inappropriately, and if poorly designed, can also waste heat and create unacceptable variability in indoor temperature, air movement, and humidity. Spaces need to be designed with more attention to detail in the early stages of design. Be easy to understand and control by occupants and managers. We need to consider how spaces will be used. And we need attention to eliminating avoidable heat gains and pollutants. In fact, ventilation and cooling need to be designed on a room by room basis, not a building by building basis, to meet potentially very different requirements of different users at different times and places within a building. This may be as simple as placing the openings in the right places, but if relying on windows for ventilation, then it is worthwhile to remember that windows are required to fulfill a very large number of tasks. They are there to provide light, they are there to provide connection, they are there to provide views, and if they are there to provide air, then the success is probably in the detail. There's plenty of guidance available on ventilation and cooling, but most buildings either fail completely to create indoor environments that are comfortable and healthy, or they consume lots of unnecessary energy to be less comfortable and healthy than they might otherwise be. In 2002, driven by a desire to know more about designing ventilation in buildings and in particular in schools, I organised a tour of school buildings in Norway. One of the first we visited had a very interesting engineer. Dagfinn stated, "Good indoor air quality is a human right." It felt like a very different fashion declaration to that which I was used to. It sounded like a fashion declaration that people with dementia and people who work with people with dementia and people who visit people with dementia would really value. It sounded like the kind of fashion declaration that teachers and school children and office workers and people who live in their own homes would really welcome. Good indoor air quality is a human right. The schools that we visited form some very useful case studies, and they are encapsulated in these two books, Design and Construction of Sustainable Schools, which includes German examples too. They are downloadable from, I believe, from the SEDA website. Any problems, ask me. I can get you them, sandy@gaiagroup.org. And then there are a whole load more ventilation and cooling examples in my book Sustainable Construction, the second edition, and actually some interesting ones in the first edition that might at some point be worth revisiting. And these include Vans to School with a rather nice culvert system and a Bernoulli effect, dynamic installation at McLaren Borhaug, and the Bareham care facility for the elderly. Building 226, housing project at Toll House Gardens, Carrickle School, housing designed as healthy housing in Zurich, Plumbers Wood, passive house in the Borders, and then there's work on the Bullock Centre, which of course had the red list for material specification, and all of that can be found in Sustainable Construction Volume 2. Thank you very much for your attention, and I look forward very much to hearing the other speakers. It's going to be a great session. Thank you very much.
I'm an architect, but I'm kind of not an architect. And Magda got in touch and said, we're going to talk about natural ventilation. And I go, oh my goodness, what am I going to talk about? And I thought, I work with nature now. So how we fit nature into natural ventilation. And what I'm going to talk about differs very slightly, but from what I've written there, but that doesn't. Okay, let's kick off. There's that. When we think about natural ventilation, we are basically designing systems at the mercy of whatever nature is going to throw at us. So that's how the sun moves around, it's how everything warms up, it's how the air moves, it's how we get shelter from different things. But that knowledge of how natural ventilation, that knowledge of how air moves around a site is something that we used to have. It used to be culturally ingrained. We used to know what our sites were like, but because we're all busy, we're all really ambitious, we end up working not where we live. We end up moving from different countries to different countries. We end up working in different countries, different regions. And so we tend not to know what the microclimate of a place is. And actually, when it comes to natural ventilation, the microclimate of a place is really, really important. My wife and I live in West Fife. where, like most of Scotland, we've got southwesterly prevailing winds. The only thing is, in our garden, the wind doesn't come from the southwest, it comes from the east because of the trees that are there on the southwest, and it all burls around. And it's taken us a few years to know it, and now we've been there for a few years, we realise obviously those trees will affect our microclimate, but we wouldn't know that if we didn't spend a bit of time looking around at that. But that knowledge of microclimates and how air moves around, best to use natural ventilation in a building. This is something that we've lost our knowledge of how to look at a landscape and how to look at which way the trees are bending, for example. And the only way we can really get that back is, like I say, to spend a bit of time there. But we also need to get to a point, I think, where we intrinsically know what we're looking at. And we don't want to, we're maybe spending too much time with spreadsheets and dynamic thermal modeling, which have their absolute place, but there's a real value in us developing our rules of thumb so that when we look at a landscape, we know how we're going to build that into a natural ventilation strategy. And this is what we end up doing. That culturally ingrained knowledge that we have, looking at nature, seeing what nature tells us, what are the signs. We ignore that and we spend lots of time talking about all sorts of really amazing technical systems. But as we do that, we ignore what nature's telling us, and we end up moving towards mechanical systems often that we replicate in terms of the details and the designs and the systems. So we're now in this weird position architecturally where we will produce a design in Scotland for a building, or in Germany, or in South America, and we will replicate that design around the world. And we will not take any notice whatsoever of what the local factors are in terms of how air moves, how sun moves, how nature moves, what the different types of shading are through the course of the year. And as we do that, as we increasingly mechanize the way that we design our buildings and move away from our understanding of natural processes, that move towards using more energy intensive systems means that those energy intensive systems are very reliant on us having a stable climate. And of course, one thing we don't have is a stable climate. We're now moving into an age where climate change is giving us, we've got wildfire, we've got drought, floods, we've got increasing intensity of storms. And the upshot of climate change and all of these effects that come from climate change are that our power systems, which our homes and our buildings rely on, the power systems are being knocked out. And there's a question really of how resilient are our buildings when we end up in these situations? What do we do when the power goes off for 3 days if your home's completely mechanically ventilated? I know we can open our windows, but if we're relying on that for our filtration system, then I don't know, what do we do? So we need to adapt. And the note I've written down here is adaptation means changing the way we operate to suit our changing surroundings. And in the building regulations in Scotland, we've seen, for example, that we now have to have purge ventilation. Building regulations now say we need to be able to open a certain size of window and door so that when it gets really warm, we can keep our buildings comfortable. And that's brilliant. But part of my provocation to you would be to say, what happens if, stop me, because these doomsday scenarios, these scenarios of the of us having power cuts, they're happening now. This isn't future stuff, this is now. It's only going to get worse. But when these things happen, how do we make sure our buildings are resilient? Is there a place in the building regulations to say, as well as having purge ventilation, we need to have a way of our buildings being able to last comfortably for 3 days, for 72 hours, like a battery backup on a smoke alarm? What's that period of time that we need our buildings to be resilient and operate by themselves naturally through good design? I'd be interested to discuss that. But this knowledge of how to use our environment to keep our buildings comfortable and cool, it has been there. It is still ingrained in some cultures, perhaps not so much in the West, but These are wind towers in Yazd in the Middle East, Far East. And for centuries, these are used in the middle of the desert, winds blowing in a certain direction to drive air down and keep spaces cool in 40, 45, 50 degrees. It's not just in hot countries, though. We see this at home. Coventry University, there's an engineering building down there that takes that idea of using wind speeds at higher levels to drive natural ventilation in big commercial buildings. This is the BRE building down in Garston, which some of you might know. This was a proper case study in the day, and it uses a similar idea. It uses high-speed wind to drive natural ventilation, and then it has these lovely vents which cool these soft. You use night cooling. Very simple, really elegant strategies for cooling our buildings, keeping them comfortable in warm temperatures. I would love to know if anyone's visited this building to see if it is as good now as it was meant to be. Yeah, I'm getting nods. Still performing well. Brilliant.
I was the consultant for it.
Sorry?
I was the DOE appointed consultant for it.
Well, it's going to be good then, isn't it?
It's working well.
This is the building I work in. Those three buildings that I just showed, apart from the first one, they're new buildings. This is Mill in Stirling. It's 9 meters wide and it's got windows on either side, and it is roasting in there if you don't open the windows. But as soon as you open them on either side, you have this lovely cross vent. The ability of some of our older buildings to be retrofitted to take advantage of natural ventilation strategies is huge. But my question to you is, when you're designing your buildings today, I don't know what proportion of you are going to be designing new and designing retrofit stuff. How are you going to retrofit your buildings you're designing today for the future so that they're comfortable? At a slightly smaller scale, this is a school which Gaia Architects and Gaia Research worked on 15 years ago, which uses the prevailing wind, the actual prevailing wind direction, to bring it in at low level at the front in the classrooms, take it out at high level at the back. That resulted from those books that Sandy talked about schools. It's really effective. It really keeps the temperature and the humidity and the carbon dioxide down in classrooms, which is where you want carbon dioxide to be nice and low so that the pupils learn. Architects like Glenn Murcutt, I'm a bit of a Glenn Murcutt fanboy. Architects like Glenn Murcutt over in Australia were brilliant for using the local knowledge from Indigenous people to go, the wind comes from there this time of year, the wind comes from there this time of year. We're going to create a series of layers on our building so that it's comfortable, different conditions throughout the year. And then we get onto nature. How does nature fit into all of this? Not just natural wind patterns, but I suspect you've all seen the reports and you've seen the headlines that say, if we put trees in our streets, then we can reduce our local temperatures by 12 degrees. It's much more than that, because the trees don't just shit, which then reduces our risk of heating and means that we need less ventilation. They also humidify the air, and so you need less plant to humidify it, and you get the benefits of wildlife on your doorstep as well. But then when we look at a smaller level, we go, what does nature do? How does nature itself design? And we look at what bees do. Bees create these incredible structures where they go, okay, we're going to build off the shady side of the tree. We're going to put layers that allow us to keep cool air going up between the layers of hives, but not too far apart, so they don't get too cool. They stay just the right temperature. Do you know what I should have done? I should have put up a picture of one of these little Spanish villages that shows all the streets really, really close together. That's cultural knowledge right there. And then, yeah, that's another one. And then there's termites. You've all heard about termite mines, and you know how they draw in cool air and they use it to drive air through the building. But one of the things these have in common, and which Sandy touched on, and I know Janice is going to touch on as well, is the materials that these are built from. These are not hard, impermeable materials that these things are built from. So what we build our buildings from is a fundamentally important part of that ventilation strategy too, to help buffer the moisture, to help store the heat and put it out when you actually need it. And that's what nature does intrinsically. Right, last thing. I work for an organisation called NatureScope. And this is a great title, I'm their net zero team leader. And we have to retrofit 40 buildings. And my challenge is how to do all this good stuff I'm talking about and build it into the architecture. So that's going to be a good challenge. Keep your eyes peeled for what we do. Thanks very much.
I won't talk at length about ventilation itself because there are a lot of expertise in the room who will do that. I'm going to talk around the issue of why it's important to get it right and who might be most vulnerable when we're thinking about designing solutions. So that looks like it's all working lovely. So yes, this for those who didn't hear online, this is really my favourite quote of the week. This quote comes from 1965, so to give a little bit of context. This is around the time when the civil disability rights movement started to gain traction, and the organisation who published this wonderful journal at the time called The Magic Carpet it became the Disabled Drivers Association, and hopefully the mic will keep working. And this quote here was in the editorial of one of the 1965 issues, and I'll read it for anyone who wants to hear. So it says, "To hell with the half-witted architect who dreams up fabulous ornamental buildings with not one scrap of common sense about them. He may be a great man or woman, but how much greater he could be if his dreams were less like nightmares to a percentage of the population." So this is in the context of physical accessibility of built environment, which is my main area of expertise. But I think it's really relevant here as well when we talk about a poorly ventilated space feels like a nightmare for a lot of people. Oh, come on, slides. We'll get there eventually. Just need to click into the screen. Okay. So when we talk about vulnerability, it's worth just trying to put some sort of definition to the word, and within the context of what I'll talk about today, it's really about people who might be exposed to the possibility of being harmed, maybe at a higher risk of that than some others. The UK government has sort of a definition around vulnerability in all our health, which you can read about online. And here talks about people who might be in need of special care, support or protection because of age, disability or additional risks in their life. So just to kind of set the scene around what we mean about vulnerable, it's that kind of people in the population who might need that additional consideration. So when we think about the prevalence of perhaps vulnerability, normally I call this slide kind of prevalence of disability, but I think using the word vulnerability is quite interesting in this context. So in the UK, approximately 25%, I think it's something like 24.9 at the moment, but pretty much a quarter of the UK's population would be considered disabled under the Equality Act's definition. Under the UN's definition of disability, that probably be bigger. But if we think about the ageing population, and we know it's a global crisis, we currently have 45% of the disabled adults are over the state pension age. So there's massive correlation between disability, impairments, all sorts of age-related frailty and health issues and disability. But by 2050, that number of people over 60 years is set to double. But it didn't have to maybe think that we as of today, as of this summer, we're closer to 2050 than we were to 2000. So that time is coming. So more of us are living longer, and there will be more aged people, but research is showing that we're not living in good health. So there's lots and lots of reasons for that, but also that's worth remembering. one of my background areas is working in dementia design, so I can talk at length about that, but I think it's important also to think about maybe within this bracket of vulnerability and people who live with cognitive impairment. So at the moment, approximately 1 million people in the UK live with a type of dementia. But again, this number is set to rise. So by 2040, we're looking at a rise from the 1 million up to about 1.4 million. And the quite startling statistic that comes quite often when I have these discussions is the World Health Organization identified that it's projected that of those children or people born after 2015, 1 in 3 will live with dementia in their lifetime. So the prevalence is on the rise as well. And I particularly liked Sandy's slide with the quote around air quality being a human right. I talk a lot about rights in my PhD, and I guess it's sort of remembering that disability rights are also human rights. Rights are rights no matter who you are or what type of vulnerability you have. And when we think about what those rights are, it's about dignity in your life, choice, independence, and the ability to have equal participation in society. So if you're particularly vulnerable, you might need additional support to do that, or additional considerations in the design process, buildings and places to be able to enact your own human right. So yeah, over the next 3 slides, I'll look at giving some examples of the way in which we might see inequalities through the use of ventilation in maybe an inappropriate way, or just not being considered fully to be inclusive. So in the case of people living with dementia, there's some quite interesting research that's come out recently, and it also is very much in line with Sandy's wonderful book around the quality of indoor air. This research is the first one here, number 1, talking about discomfort. When you're sitting in an environment, the indoor air quality is poor, you experience discomfort. And basically some really recent research has indicated that that level of discomfort within a care environment is very much likely to increase. The article uses some slightly questionable terminology around behaviours, but it's likely to increase stress and distress behaviour responses. So from a carer perspective, it will become a little bit more difficult to support people who experience this sort of indoor discomfort. And as somebody who's living with this cognitive impairment, you are stressed and you don't know why, and you find it difficult to express that reason. So that's one of the really important reasons to think about this type of outdoor air quality. And if you think about a care setting, there are lots and lots of ways that you can be dehumanized in that setting, and that kind of lack of control. You know, you're sitting maybe in a common area with some people wanting windows open, some people don't. There's probably lots of mechanical systems going on that you don't have control over. You've no idea what the temperature is in the space yourself. So this is just another level of that, kind of thinking about that extra level of care whenever we're thinking about that type of institutional type of setting, but also thinking about people who are at home who are living with a cognitive impairment. You know, they spend an awful lot more time indoors than outdoors, and there's a lot of work around trying to change that. But this idea of, you know, somebody sitting in their living room in the same place all day long, there's coming into the evening time, there are a set of symptoms that are described as sundowning, where people can become particularly distressed. And one of the reasons is that they may be sitting there too hot all day, too cold all day. Poorly ventilated spaces will just make it a horrible, stuffy, smelly environment. So again, it's just thinking about that from that perspective of individuals who aren't able to really recognise what the issue is to themselves. And the second point here is another set of research that looks at how the quality of the indoor air can actually, for people who might develop vascular dementia, the risk is increasing. And this is to do with PM 2.5, particularly the research. The links are here on the slides, but if you're interested, I can send that through to you and have a really good detailed look. But that idea of indoor air quality being with a potential causal link, you know, we know in terms of increased instances of children living with asthma, but there are so many other things we maybe don't know yet. So in terms of people living with dementia, vascular dementia has been identified as a particular risk whenever you're sitting in a poor indoor air quality area for a long time. And thinking about controls, this is maybe kind of a common sense type of thing. But if you're somebody with reduced mobility, for example, you might not be able to easily access vent controls. You might feel disempowered by that, and that might increase your reliance on support, where otherwise you might be very independent in your life. If you can't reach the trickle vent at the top of your window, or the window behind your kitchen sink because you've got a counter in front. I myself know that just through experience of having a giant baby bump in the past, and that's coming to me soon. That idea of the disempowerment that's experienced by people who find controls inaccessible is massive. And there's lots and lots to go into detail there, but I'll keep moving on. But the other end to think about is people who live with reduced mobility, again, spend a lot more time in an indoor environment, and they're much more susceptible to developing related health conditions, health illnesses, because they are spending that much more time indoors as well. So there's sort of the duality of issues happening there. And when we think about thermal comfort in relation to ventilation, again, another kind of common sense slide, but thinking about even from not just older people, but thinking about infant babies and children and the risks they face if they're in a space that's too hot for them or too cold. This is all related to the getting the systems right and getting them user friendly, and thinking about that range of people who are going to be in a space. So I talk a lot about housing and care environments, but then if we think about schools, as we've mentioned as well, and a P1 child in a classroom isn't going to raise their hand and say, I feel stuffy in here, can we open a window? They're probably less likely to be aware of that being the issue for them, but they might exhibit that through their behaviour and their lack of ability to learn. So again, it's something that's really important to consider when we're thinking about that whole broad spectrum of humanity and trying to be inclusive. So when we get to the kind of who cares part, I'll not be able to go into lots of theory around disability theory and what the social model is, but in a very quick snapshot, the social model of disability situates disablement as something which is a result of external barriers which interact with a person's impairment or health condition. We must understand the disabling power of the built environment, that people are disabled by barriers in the built environment. And that's really the message to architects whenever you're thinking about creating accessible spaces, when you're thinking about creating spaces that actually cater to people's needs or are considerate of a range of needs. It's the power of the built environment to disable people is really massive. And so I've kind of reiterated that point here when we think about the cross-section of our population and the disabling power of the built environment. That's why it's important to architects and designers of places and anyone responsible for the built environment, because the social model of disability is not a new concept. It's been around since the early 1960s and defined formally in 1983 as a term, but people have been talking about the reason why they feel so disabled is from all of these external factors. And so the kind of final quote of my presentation is around the World Bank and the World Health Organization's report on disability. The last one they released was back in 2011, which feels like quite a long time ago. I think there should be an update, but that and the UNCRPD, the UN Convention on the Rights of Disabled People, they all identify the environment as having a huge impact on the experience and extent of disability. So again, anyone who's involved in the creation of the built environment, you need to be aware of the power you hold in that place that you work, and that it might happen to you one day as well. It's not just for othering and other people. Disablement can happen to anyone at any time. So it's just a really powerful message to take when we're thinking about ventilation of spaces and why it's important. So thank you.
I'm hoping the case studies that I'm about to show you will segue quite neatly with presentations we've already had, because all those, whilst I'm going to talk about a couple of things which are probably quite pragmatic, buildery solutions, architect solutions to problems, hopefully there's a sense that the issues that have been discussed, I wouldn't say I was consciously thinking about them at the forefront of my mind when I was working through all this stuff, but I think there's a lot of things that do match. I did realise after I put the slides together, there's actually a third case study I could have shown, which is a private house. These two case studies are both commercial buildings, a retrofit and new build. And I forgot to put some slides in for that. But if anyone's interested in that, there's actually a little interview that I do with my friends Alan and Joe, whose house it is that I designed in Burnt Island, and that is almost entirely passively ventilated through the use of high space and beneficial solar gain, which you'll see again in these case studies. So the first one I'm going to show, this is a project called Norton Park. Many of you will have been bored to death of me talking to you about this project over the years. So apologies for that. I'm not going to go on and do the full 9 yards. I still lecture on it. I was the project architect from inception all the way through to completion when I worked for a practice called Burnett Pollock Associates back in the 1990s. And I am now actually a trustee of the Norton Park Trust that own and manage the building. And as you can probably see from these two, it's an old Victorian school. Again, I can lecture for 2 hours on this one, so I'll cut to the chase. But one of the really interesting things about school design from this period was the prompt for all of these buildings being built was the 1870 and the 1872 Education Act, one in Scotland, one in down south. And the greatest number of schools were built by the London School Board. Each major city would have a school board, and the guy who ran that with a team of about 15, 20 people built something like 300 schools in a couple of decades, and wrote the case study or the how-to book, the design guide of this is what a school looks like. This is why they're so consistent. They might vary in external style, but actually when you look at them, they're really consistent. And that's partly because although Edinburgh had its own school board architect, a chap called James Alexander Carfrae, all of the designs had to be approved by the Scottish Secretary of State for Education, who of course was based in London and had obviously read the textbook. But one of the things about all of these buildings is, and you see it in a lot of other Victorian buildings, very high ceilings and sash and case windows, which give you a circulation of air. Why high ceilings? Class sizes in the early 1900s, late 1890s, etc., would be 60, and nobody had any indoor plumbing. So these were quite smelly places. Huge benefit in terms of metabolic gain. They also had pretty inadequate heating systems, but that's another 15 minutes of slides that I'm not going to bore you with. This is quite an important slide because one of the main interventions we made was to put these galleries in the ground and first floor classrooms. The ceiling height was good enough. That creates in itself, I mean, it created huge benefit economically, but it did create a huge challenge from a ventilation point of view because you're going to get stagnant air at the top level, which I think Sandy was talking about in her presentation. Unfortunately, the bunker fans that we're going to put in were lost as part of a cost saving. However, one of the things we did do, and you can't quite see it from this slide, but we massively improved the levels of fabric insulation. So insulation in the walls, secondary windows, which in themselves are double glazed and achieve a U value of 1.1. This is all back in the mid 1990s. We drastically reduced the amount of heat loss. What I didn't want to happen was people would come in the morning and feel chilly and turn the heating up, and then feel stuffy and open the windows. However, at the same point, I didn't want people to not have the ability to do that. I think Sam touched on this about the ability that people should have to be able to control their environment. Psychologically, it's really important. There's loads of studies that have been done which show when you take that control away, people get very mentally uncomfortable, even if actually they're sitting at what might be deemed by SIBSE as the ideal temperature. Picking up on something else that Sandy said, when I was doing my PhD, one of the bit of researches I came across was a whole bunch of stuff about how the air conditioning industry, primarily in America and through the setting up of ASHRAE, which is a bit like their SIBSE, how they had marketed air conditioning at increasing productivity. And of course, it was all to do with selling more kit, or as engineers, getting the opportunity to design more kit, exactly what Sandy was talking about. Anyway, so rattle through this quickly. So I didn't want people to come in, feel cold, put up the heating, feel stuffy. So one of the things that we did do was put in a background ventilation system. So there are some air handlers in the building which provide roughly 1 air change per hour to these big spaces, which is a tiny amount of air to actually move. Whether I'd quite do it this way now, 25, 30 years on, matter of debate, but just enough to keep it hopefully fresh for most of the time. Obviously the windows all open, so in the summer when you're not heating the building, open the windows. And on the ground floor and the first floor, they have mechanical heat recovery as you'd expect. It also does on the top floor. It's 3 floors mainly, but the top floor also benefits from a solar slate system. And this was developed. The ideas behind this were developed by a guy called Kerr McGregor, obviously 20, 30, 40 years ago. Sadly, no longer with us. Really, really clever and interesting guy. And where he was coming from was looking at how you control buildup of moisture in older housing association, local authority flats and houses. He was looking at MVHR as a moisture control more than how it's being promoted at the moment, particularly looking at popping these things into communal stairs in blocks of flats. And what this does is it sucks air in from underneath the slates, and that is the intake air for the top floor MVHR system or air handler. Obviously in the summer when it's warm, it clicks over to fresh air elsewhere. You don't want to bring in warm air. It's astonishingly efficient. So this is a bit of the building has been heavily monitored by both myself and others. This particular slide comes from around 2000 when the BRE monitored it, and it shows over a period of time in the middle of winter, the air temperature coming off underneath the slates, which act as plate heat exchangers effectively, and the outside air. So there's one day in there. Those of you online, I'm about to point at the slide. You won't be able to see it, but it's the one where the lines are at the top. So I think it's somewhere over here, sometime in January. Outside air temperature is 0. The air coming off the underneath of the slates is 21 degrees centigrade in January. It's one of those really bright, sunny winter days. So you don't need any additional energy to heat that air. It makes a huge difference. Now, I also got the opportunity when I was doing my PhD to go back and do post-occupancy evaluation of the building. I did that using 3 different methodologies, more to learn about those methodologies than the building, but we still learned some interesting things. And one of the things that I was able to do was to monitor temperature and relative humidity in some of the spaces. Not as much monitoring as I would have liked to have done, but still it's there. And these are the results. And this is taken from the hottest day of the year, which was also the day I did the building user survey. And again, for you online, I'm about to point at this slide again. But most of the monitoring equipment was in the southwest corner of the building where there's a lot of glass. And I knew that there was an issue of excess buildup of heat because you've seen the sides of the windows, they're pointing southwest. You're going to get a lot of solar gain. So the line at the bottom, if I remember rightly, is the reception area in the building, which is actually in the middle of the building. You come in, go quite a way through, and that's relatively cool. It starts at just over 20 degrees, and by the end of the day, it's at 23. So, most people can cope with that. The next line up, which goes up in a hump, comes back down, that's the conference room. And that's at the back of the building, but they had a meeting that day. So that's the effect of metabolic rate. So it got quite warm when people went into the meeting, and then it gradually tailed off and cooled down. The worst one was the mezzanine on the first floor. So one of the really high space where all the air is stratifying up to the top. And that's the top line, which, as you can see, starts at nearly 25 degrees or 24 and a bit. And it's over 26, nearly 27 degrees by the end of the day. So it's building up a lot of heat. And I know that had been a problem. And I also knew there was actually a solution, which the facilities team managing the building, this was done in 2014, 2015, had forgotten because they hadn't been told by the previous facilities manager. And as part of the post-occupancy evaluation, alongside doing all this monitoring, the user satisfaction questionnaire also allows people, it does loads of Likert scores as always, but it also allows people to make comments. And predominantly from the southwest of the corner, there were all these comments from people saying, it gets too hot in the summer, but my colleagues won't let me open the windows. I mean, that's almost a direct quote. And you can see that it's getting to 20 degrees. what the facilities management team in place at the time had forgotten, or hadn't been told by the previous facilities managers, was all they had to do to help, not solve, but at least reduce the impact of this issue, was at night go around and open all the inner windows. So you've got an outside window of sash and case, got a U value of 5.7. You can leave that closed, but you've then got another window on the inside with a U value of 1.1, which you can open without any impact in terms of rain or wind or whatever. And overnight, you're shed 4 degrees. So the facilities team have now been reminded of this, and that's what they do. It provides a zero cost management solution. And one of the things I think is interesting about that, and it goes back to the discussions I was having with the client right at the beginning, is having the opportunity and taking the time to have a risk-based conversation with your client about whatever you're designing. Some clients are incredibly risk averse. I've had clients say, look, I want you to give me a system that is turned on and I never touch it and it does everything for me. I usually say at that point, I don't think you're the right client for me, because if you're not prepared to manage your own building, don't expect the best possible results. But it reinforced some of that sort of risk-based conversation that I had with the client, and which I'll illustrate with the next case study. I've got, I think, one more slide just for this. Yeah, one more slide on this one. Again, what you get from a usable building trust post-occupancy evaluation, you get many things from it, but you also get a very neat summary where across a series of issues, they will give you a score relative to your peer group. And if it's green, it means you're scoring above what they see in the peer group. If it's orange, you're there or thereabouts. If it's red, it's a bit below. And bearing in mind, a lot of the studies that I've done have been for educational buildings, because it used to be part of the funding for new build educational buildings that you did one of these, and academics just like doing these sort of things. So predominantly they're across education buildings, and predominantly a lot of those buildings will have started out with some green aspiration attached to them. And what's really interesting about this is it scores very well on things like the design. Thank you very much. Admittedly, I didn't design the original building, but I'll take the credit. It meets their needs, etc., etc. But the ones that it scores badly are temperature in summer, overall a bit uncomfortable. Same for the winter, and overall productivity is perhaps low because of that overheating. Now, like I say, this was done on the very hottest day of this particular year, so people were probably quite grumpy at the time, and they hadn't rolled out or forgotten the solution to it. But again, it comes back to what you've heard in presentations before. People's comfort levels directly impacts on their sense of well-being, their productivity, their learning outcomes, their health outcomes, all of those things. So it's vitally important to get right. Would I do it this way now? I mean, this is getting on for 30 years ago that this was being designed. I'd certainly do some things differently. I'd still want to have that same risk-based conversation of how are we going to make this work? How am I doing on time? Am I okay? On to the second project. This is a building, the Tallis Russell Environmental Education Building in Fife, which was completed in 2011. Therein lies another tale. But a brilliant brief to be given as an architect, which is design a building which explains, hopefully, or is as sustainable as we can make it, and then explains how it does it, and has an exhibition that looks at all of these aspects. I should have said with Norton Park, by the way, part of the brief in that we did a huge amount of work of specifying the most benign materials we could possibly find. So natural fiber carpets, silicate paints, etc., etc. No, there was virtually no preserved timber went into Norton Park, other than the windows and the glue lamps, which we couldn't stop being preserved. And that was applied to this building as well. So lino flooring instead of vinyl flooring, all that sort of stuff. Linseed oil paint instead of white spirit-based paint. Jim Johnson, our friend and late Jim Johnson, said a wonderful thing when he visited on a SEDA event. He walked in and he looked for a few minutes and he said, "This smells really nice." And that's genuinely one of the biggest compliments I've ever had, because we all know what the smell of a new building is like, and that's all that chemical shite that Sandy was telling us about that goes into buildings. The form of the building was driven by, to a certain extent, entirely by the ventilation needs. And as a brief, it was really challenging because the hope was that every school kid in Fife would have at least one school visit during their school year to this, to time in school. But for long periods of time, the building would probably sit relatively empty, a few meetings happening, a few small groups. And of course, those visits and those evening visits could happen on the hottest day of the year when it's nice and dry, or it could be on the coldest day of the year when it's pouring with rain. And again, I had a lot of risk-based conversations with the client, and it was all down to, I want to give you a building which, to do what you want it to do, you will need to manage it, and you will need to learn to manage it. So you will need to learn over a period of time. If we've got a coach of school kids coming and it's late March and it's a bit drizzly, what I need to do before they get there is this. If it's in the middle of summer, what I need to do is do this. And as a building owner and manager, you need to learn that. It's back to Sam and the microclimate and the wind goes around the trees. Of course it does. You have to know the building for a period of time. You have to learn that and learn what you do in certain circumstances. So again, in terms of risk-based, slightly tangential, but I'll come back. One of the risk-based conversations that we had is the boiler is too small for this building. It has a wood chip boiler. I'll come to the had wood chip boiler, which is too small. Why is it too small? It's not mission critical. This sat in a campus of many other buildings. If it's really, really cold, you've got 2 foot of snow on the ground, you ain't getting those school visits. So you don't need the building sitting at 21 degrees. If this was a nursing home, you'd have 2 boilers with a level of redundancy built in, because if people get cold, it can kill them. So again, a risk-based conversation of why are we putting this stuff in to make a building to do this when you're never realistically going to use it in that way or at that time of year or in that particular purpose. So on to the ventilation. And there are mechanical ventilation systems in this, in similar way to Norton Park, which is how do you provide enough ventilation at the critical point when it's needed, but isn't in use all the time. So the control systems, again, Sandy talked about control systems. The control systems were hybrid. There was a control system which was manual to turn it on, and then there was a control system which was automated, which was constantly trying to turn it off again. So that was reliant on CO2 detectors within the extract system, because that's indicative of the number of people in a space, in a room. If the CO2 goes up, it's getting stuffy, so you want your ventilation on. But if there's nobody in that room and your CO2 says no problem here, it should be turning the system off. We had movement detectors. So if we had one big conference room or a presentation room, which was a fundamental requirement of the client. If everybody on a school trip goes in, sees a film, has a presentation, then goes out, gets on the bus, drives away, movement detectors say there's no one in this room. Right, I'll turn the ventilation off. So it's all about having that conversation with the client to say, how are you going to manage the building? How do we put in controls that will help you manage it in the way you should, but also be aware you're going to have to be reliant on manual controls. And I'll just quickly go through how the building mostly passively ventilated. So one of the things we did, obviously built an architectural model, and we did a 365-day sun analysis. So we ran a program which showed how far the sun penetrated into the building in the middle of summer, in the middle of winter. And that dictated the overhang. The building faces southwest. The main glazing that you can see on the bottom left-hand side faces southwest. So that overhang is designed to ensure that in the winter, the sun gets all the way into the building. There's a solid floor, there's a solid wall at the back, lots of thermal mass, soaks all that stuff up. In the winter, you get significant amounts of shading. You don't get too much in the way of solar gain or glare. The other thing about that elevation, bottom left-hand corner, as you look at it, the front of the building is formed from a solar chimney. So you've got 2 lots of triple glazing to create a slot. And that slot creates obviously a vertical column of air when the sun comes out. And there are vents at the top and there's vents at the bottom. So in the summer, when it's hot, you open the vents at the top and the vents at the bottom, and then the vents on the north side, and you pull air with stack effect right the way through that big space. In the winter, you can close it all up, and you've got 2 lots of very high performing glass between you and the outside world. I don't think the building ever dropped below 10 degrees centigrade with no heating on. The other thing you see in the slides on the right hand side, I touched on this before, there's 2 air handlers, one for the big space, one for the conference space. And they are oversized, they're deliberately oversized, so they can run very slowly, which makes them very quiet. But it also means you can control the speed. So you can control the speed relative to the CO2 system, CO2 level in the air that you're extracting. And again, the control is all about, okay, if you want me on, I'll come on. But if I decide you don't need me on, I'm going to turn off. And if I do, and you want me on, you've got to turn me back on manually. Again, it was all this idea of, I've got a coach party of kids coming. They're all going to pile into that conference room. Because of its shape, you don't have a huge amount of vertical space in it. It's going to get stuffy. I'll turn the air handling on so it doesn't. And then it will turn itself off when they disappear. So, yeah, that was the tree centre. Now, all of this is good, and you may be wondering why none of you have ever visited it. And this comes to the last slide, which is, if you have an unsustainable business plan, you end up with the ultimate form of natural ventilation. So it's no longer there. Which is very sad. But there you go. That's me.
Yeah, so my publication was about that we quite often get people ring us up. So I kind of like rewind a little bit, because not everybody in the room knows who I am, where I work now. So I don't work as an engineer anymore. I'm a researcher here at Glasgow School of Art in the School of Architecture. And the research unit was set up 32 years ago to do building performance evaluation in occupied buildings to see how they perform. And if and in particular, when we first started, we were looking at existing buildings which had lots of mold, but more recently we're moving on to newer buildings which are overheating, they're getting too hot, they're uncomfortable for people. So we go out and we measure pretty much everything you can think of: the temperature, the relative humidity, the carbon dioxide concentrations, the indoor pollutants, the volatile organic compounds, which you might have heard about, particulate matter, daylight, energy, all sorts of different things we check to see how things work as well. And so, you know, we build up this big bit of knowledge. I've been sitting here and all I can hear is that. I don't know how other people, so yeah, the ventilation in here, to me, as a services engineer, isn't designed very well, because we shouldn't be able to hear that as we're in this room. So we get quite a lot of people ringing us up and saying, you know, low energy housing, do I have to put MVHR in? Building regulations are forcing us to. So I'm going to give a case study of a project that I worked on to see what insights we can learn. So, hold on a minute. Yeah. So I'm going to take us all back on a little journey 10 years ago. This is at a time when we were, we had an event here in the rebuilding downstairs, which was disseminating the building performance evaluation work that we've been doing. But one of the things that we, you know, there was lots of things, and I'm separate because I could talk all day about the work that we've been doing. So, but one of the things at the time as well, there was a lot of conversations about whole house ventilation, so mechanical ventilation with heat recovery. It was a hot topic. People were really nervous about installing MVHR in buildings. Housing associations who have a responsibility to provide really good quality houses for their tenants were really nervous and not wanting to install mechanical ventilation and heat recovery. We worked with Andy as well on projects as well. But there was also, alongside that, the reports were the MVHR poorly designed, it's poorly installed, it's poorly commissioned. And it was, yeah, and we saw that when we went to places. So this is one house that I went to have a look and check up on the ventilation system. This is in a loft. You can see the rafters. How are people going to get there? These are the filters on this that need to be changed or inspected once every 3 months. So you can see why people were kind of like a bit nervous about it. And we would measure the flow rates, the supply and the extract, and we'll find like huge imbalances between supply and extract. So there were lots of operation issues. There was inadequate handover information, so people didn't know how to operate it. What should they be doing? What buttons should they be pressing? And it was just people were just unclear. Like, who's responsible for this? If I'm a tenant in a house, who's responsible for the maintenance of it and the filter replacements? And then obviously poor access. This isn't just in Scotland, this is UK wide. So we have projects in London where we had problems with ductwork, we had all sorts of different issues. So that was 10 years ago, and we had that event. After the event, we had a phone call from the Ganachie Trust, who are based in Perth. And they said to us, we're building 48 new houses in Perth. Can Miru, which is the research unit where I work, come and help us to design a natural ventilation strategy for our buildings and input the knowledge from all the lessons learned from the building performance evaluation? So we were, okay, yeah. So we found out a lot more about the Ganachie Trust, and we worked with, we had background information, we met them, and then after we met them, we were introduced to the design team and Jess, we worked with Jessica as well. And so Miru were embedded in the design team, which is quite unusual, to impart building performance evaluation information, and also to help kind of talk about the building and how do we create a building which is kind of less harmful. And so we had funding from the Ganachie Trust themselves and the Construction Scotland Innovation Centre, who are now best. But the Ganachie Trust was set up, and the first houses that were built there on the estate were in 1923. And in 1923, A.K. Bell, who was the owner of those houses, he was really adamant that ventilation was key to health in these houses. And this was a plaque that was in every bedroom 100 years ago. 100 years ago. Ventilation means health. And Jessica touched on that earlier with the inequalities. So we formed this collaboration, and we had workshops and design team meetings, and we wrote a guidance document which was available on the Construction Scotland Innovation Centre website, which gives all the lessons learned from the BPE. And the design considerations were natural ventilation, looking at the energy consumption, looking at building materials that are more benign, to make sure that the indoor environment quality is good. So we check daylighting levels, daylight factors as well. And once the houses were built, to go back and do building performance evaluation to test them to see if they're working as they should do. So as part of the design, we were testing lots of different ideas come up and tested the design proposals using a dynamic model, and we used dynamic simulation. And I was looking back through a little book earlier. I performed over 400 iterations on one house type. You know, so it's really involved. It's really intense what the work that you do with this. So as part of the design stage, we talked about materials. We talked about how to select materials, as Richard had mentioned, wood fibre, paints, non-toxic treatments, underground insulation. We talked about loads of things. We talked about windows, double glazed, triple glazed, timber, PVC. PVC's out, so timber frame windows. But the biggest conversations that we had was around ventilation, because ventilation means health. So we did a lot of background research, and we worked quite closely as well with the architects, and we worked closely with the building services engineer. And we came across, you can see it again. Sorry, people at home, I'm just pointing to above the window on the slide. So there's this vent, and so instead of a trickle vent, there's just one big long slot that goes over the window, which can be opened to allow just a slow trickle of air, as Sandy had mentioned in her slide. And that was coupled with a passive stack ventilation system, which is controlled by the CO2 measurements in the bedrooms. So as Richard had mentioned, the CO2 levels, you want to try to keep them as low as possible. And at the time as well, through our research, we've been doing quite a lot of work about ventilation in bedrooms. That people, you know, when people are asleep, they can't adjust the windows. The ventilation in bedrooms came into the building regulations as well, so we needed monitors. So we connected it up to the bedroom with a control, which the simple control, 2 buttons, so it made it easy to operate. But alongside that, we talked about shading. So all of the front elevations of these buildings face southwest. So there were large overhangs, and we did the dynamic simulation model to see whether it would feel dark within those spaces, to check the daylight factors. So the shading keeps the sun off, which means it keeps the heat out in the summer, which is helping to reduce overheating. So the architects made a lovely feature at the front and the back of these houses as well. So they call them situtories. So people can sit outside and sit and look at people walking by, but also at the back of the houses where they are, people actually put their washing out there when it's raining, so they've got shelter. So it provided a really good environment. Also, we talked about a roof light on the buildings, which was allowing to help purge vent in the summer for when it's warm as well, so people can cool the houses quite easily overnight with night ventilation. But one of the biggest things that we discussed was the ceiling height. What should the ceiling height be? We ended up with 3 options, and this was our midway option. And so you can see that the rooms have quite high ceiling heights. There's a large volume within those spaces. So that formed the strategy. So with the building performance evaluation of the houses that were built, there were 48 constructed. There were 3 house types. So there's 1-bedroom house, 2-bedroom house, and a 3-bedroom house, which all of them are lifetime homes. So people that come in to live in these homes, the homes are easily adaptable to suit the circumstances of people in the homes. And you can see they've all got those little chimneys on, so the passive stack as well. So yeah, there's so much data on these houses. So we started monitoring in 2020, and then COVID hit. So that had to be halted. So we finished, we picked it up again in 2023 and finished the monitoring last year. So with the overheating study, got all the data, did all the calculations and looked at that. So data was collected every 5 minutes for a whole year from on the second level. And so that was a lot of data to go through. But there was no overheating, not one occurrence of overheating in any of the 8 houses that were monitored, which was great. There were southwest facing rooms, which was really good. The carbon dioxide concentrations in the bedrooms. So this, then a point at the graph. So this is showing green. So the dark green is the ambient, what it is outdoors, and the light green is just kind of going up to 1,000 parts per million. So anything which is less than 1,000 parts per million is really good. The indoor air quality, the carbon dioxide concentrations are really good. The bedrooms as well. I remember when I first walked into one of these bedrooms, we actually did a mock-up in one of the sheds at the Ganachie Trust of the bedrooms and a bed, put a bed inside it to see how much space there was, and we've been there. This is one of the bedrooms, and I walked into the bedroom and I was amazed. I've been to so many social housing projects, and the bedrooms are so small, and you know, some people have to have the bed pushed up against the wall, or there's so much. There's even an armchair in this room. You know, there's just so much space, and with the higher ceiling height, there's a big volume which is giving, which is also helping with the ventilation, and those over window slots are in the bedrooms. So, so it's all part of a strategy, you know, a combined strategy. We also looked at the mechanical systems which are in the house, because obviously for building regulations, you have to have the extract fans in the kitchens, the bathrooms, and utility rooms. Every one of these houses also had a separate utility room, which was big enough for the clothes area to go in, so people can hang their clothes, and everyone had an open window as well, so they can open windows. And yeah, so we tested all of the extract fans for their flow rates. We asked people how they worked on them. And people, these were meant to be continuously running, but they were operated intermittently. So people had gotten used to how they operated them before. But one of the biggest problems that we found was that to measure them, I was saying it was up there. I'm not climbing up a ladder to try to get to that point up there. So I got the housing manager along to help. I said, sees on the shoes and someone's worked up in their kitchen, and he can still barely reach with the kit. How are tenants supposed to keep these clean? These have to be cleaned and maintained, and they can't do that. So even though it's a really good project, there's still a few things that, you know, we can learn from this, and put the extract fans lower down so people can clean them. And the Ganachie Trust have said, yeah, that's a problem. Okay, we'll deal with it. We are going to do the maintenance on these fans in every house. So they're going to go around and they're going to clean them. Because they said, how can our tenants get up and do that? So just to kind of recap, the design strategy aimed to reduce indoor pollutants. It wasn't just about the volatile organic compounds, it's also about the heat and the humidity, which is all indoor air pollutants, and also, yeah, for the ventilation. Overheating wasn't measured in any of the homes, and CO2 was within acceptable limits. But the dynamic simulation, that was key to, you know, helping to inform the design all the way through. And yeah, there was just so much information that we got from that. So, the collaboration was really successful between the client, the contractor, the architect, the service engineer, the quantity surveyor, because the contracting team had been taken on right at the very, very start of the project. So they understood what the goals were of the project, the importance of it. They were in the workshops that we held as well. And most importantly, the occupants knew how to operate all of the systems. And I think I'm just going to leave it there and answer any other questions, but I put a link, you can take down that number. So this is on our GSA, it's our research repository. And this is a link to the report that I wrote as part of this project, which is lessons from building performance evaluation. So thank you.